In engineering, there's kind of an old rule that says your opinion doesn't matter. I've said this before, and my opinion doesn't matter, that's for sure. But what matters is what you can measure. What's been going on lately is there's been a lot of talk about Rust is better than C or C is better than Rust. Rust is safer, C is dangerous. You've heard all this before. None of this matters unless you can actually generate the machine code from both languages and compare not only how fast it is, but the other thing you need is accuracy, how accurate it is. If the answer is wrong, it doesn't matter how fast it is. This isn't a new problem. Back in the 1960s, when Fortran compilers were evolving in Watt 4, Watt 5, Fortran 66, 77, and then the new languages like PL1 and COBOL, and then BASIC and Pascal, on and on and on the languages went. Algo, can't forget Algo. Does the code run fast? And does it produce the right answer? I mean, that's kind of the whole point, isn't it? There was a British engineer, Roy Longbottom. He solved the problem for everyone. Yeah, he did. He doesn't get much credit, though. He didn't write synthetic benchmarks. Instead, he wrote benchmarks that pushed real hardware in real ways. And he found all ways that, he could find valuable results from it. But one of the questions he was asked is, how do I compare the results from two different compilers that are totally different languages? I mean, the people were asking, I want to move to this language from this language. How do I know it's worth my time and effort to do it? So, yeah, that was one of the things that he started working on. And so what he did was he looked at the whole aspect of accuracy and being able to actually put that in a form where you would be able to extract it later. Checksumming not just for the answer, but also the algorithm that created it. In other words, did somebody go in and mess with the algorithm? Or is it the same algorithm that the benchmark was published in? I think the beauty of Roy's work is that it's timeless. I mean, the algorithms don't care. You can run a PDP-11, a Cray, you name it, even a Raspberry Pi or a modern AMD Ryzen like I'm doing today. That's exactly what we're going to do today. We're going to compare a pure C program, that is, there's nothing embedded in it that's coming from Rust. It's pure C, and we're going to compare it to a pure Rust version of that same code. In other words, we're going to take and copy the C as best we can over to Rust. We're going to translate it over to Rust. We're going to have the same algorithms, the same data types if it's possible. We're going to use the same order of precedence and operations so that we don't make the mistake of, that's how you get inaccuracies, is that you make assumptions on the order of precedence. There's no foreign functions in this. We're not calling C directly from Rust, so it's not a FFI. It's not embedded in it. Basically that would be cheating. And no, we're not going to cheat. So we're going to take four of Roy Longbottom's programs, the classic benchmarks like Dhrystone, Whetstone, MemSpeed, and Mandelbrot. Now, Mandelbrot isn't one of his, but it is a modern one. The other one I'm working on is Livermoor Loops. So what does Dhrystone really tell us? Well, it's dealing with pointers, but more importantly, it's dealing with strings. The year that was written, strings weren't as important. Numbers were important. Today, it's just the opposite. It's the string that is more important. So yeah, it has actually more meaning today than it did back when it was written. Whetstones is floating point. It's math and the ability to execute all kinds of different kinds of math. So, and to be able to do it accurately and do it with what we call compiler stability, which means floating point is not precise. There's a guesstimate, an estimate that goes on between translating between binary and floating point. So you get some rounding errors with it, and that creates inaccuracies. Yeah, also Mandelbrot, that one has checksumming and a speed. So it tells you how long it took to draw the Mandelbrot. You give it a size, it generates it, and then it tells you how long it took to do it. But it also tells you how accurate the drawing was. So first, let's take a look at Roy's tests and find out what they revealed. We ran Rust and C side by side. And so in this benchmark section, we're going to look at, we'll start with Dhrystones first, because this one exposes pointer behavior. And that, I think, is going to be critical for Rust, because Rust is trying to manage the safety of those pointers. So there's extra code that's going to run before it allows the pointer to be accessed. In this hardware, we have a pure C version that we based all this off of. It completed its run in about 12 nanoseconds per operation, delivering roughly 82 million Dhrystones per second. So what, right? That's just a number that's held there. But how did Rust do? Well, Rust version, I'm just going to emphasize this, we try to do a line-for-line match with C. And then using the same structure, we came to about 94 nanoseconds per iteration, or about 10 million Dhrystones per second. So you can see these are wildly different. C performed at about 8 times the performance of Rust. I think the only reason for that would be the safety check on the pointers, right, to make sure we weren't jumping outside the program and all that. The winner of that one goes to C. So next we have Whetstones, and this is mathematical foundations of computing. These are floating point operations, polynomials, approximations, trigonometry functions, exponentials, algebraic stabilities of the compiler, all that stuff's tested. So again, pure C version was the standard we used, and we tried to mimic that in Rust. And then C delivered about 11,500 million whips, or Whetstones per second, versus Rust was about 13,000. So Rust in this case performed better because it was dealing with actual objects and addresses instead of references. So yeah, the safety checks didn't have to come into play. And I think this also suggests that, the LLVM model upon which Rust sits is actually better at floating point code generation than GNU-C is. So yeah, next we're going to move on to memory speed and find out what that's all about. That measures how fast each language can move data, reading, writing, copying, double scaling, all that sort of stuff in a tight loop. So this isn't about language. This is about memory. This is trying to force it so that it gets bigger and bigger and bigger until it pops out of L1 cache, and then it gets bigger and bigger until it pops out of L2 cache and starts to hit main memory. That's where we want it, and that's where we see the biggest drop in performance, as we would expect. C delivered high throughput in the small arrays, well over 200 gigabytes per second, whereas Rust managed about 36 to 60 gigabytes per second, depending upon, there's a bunch of tests that are done in here. So depending upon which test it was, it did better or poorer. I think that has to do, again, with the managing of memory to make sure that you're within bounds. Mandelbrot, this one is kind of interesting because it tests everything at once: branching behavior, integer math, floating point, and most importantly, it produces a checksum that not only checks the answer, but also the algorithm used to get to that answer. So if you go in and alter the code, you're going to alter the algorithm. So, and that is where we ran into some problems. So this probably needs to be revisited by me to see why we had such a differential in the checksum. So let's talk about the results first. C rendered on a 2000 by 2000 pixel Mandelbrot set it took about 1.7 seconds. It was extremely fast with a checksum of 690, 497, 749. Doesn't mean anything by itself, but if you go to the Mandelbrot game page, you'll find that is pretty close to being in line with their calculated result. That indicates that, yeah, we were kind of close to the code. Not exact, but pretty close. Rust, on the other hand, was faster. It was 1.59 seconds with a checksum of 590, 809, so a little higher. And the checksum should be about the 400 level. So it was close, but no cigar. It wasn't identical. So it indicated there was differences in the algorithm somewhere. That run produced visually correct fractals as far as we could see, but obviously there was some slight differences in it, enough to throw the checksum off. So Rust and LLVM take stricter approaches in some cases, and C compilers may fold or reorder expressions more aggressively. And that's exactly why the checksum-based tests are valuable, because you learn not only what's important, but you learn what you're comparing against. So Rust is not universally faster than C, at least in my test, but we don't have the definitive check here. So we did check pointer heavy test, floating point workloads, memory bound workloads, numerical stability, that was through Mandelbrot. And I think this is why Roy Longbottom's benchmarks are still valid today, still relevant. Because they care about the actual machine code that ends up running on silicon. Now, all of this leads to kind of an interesting point, because while we've been comparing Rust and C, the context of Linux is that there's an entire operating system out there of things that run that you may choose to run. So, yeah, trying to pick the right things and the right architecture, you may find on yours Rust is faster than C because of the libraries that are deployed. But in this case, what we're looking at is a new distribution that is completely written in Rust from the ground up. It borrows heavily from Plan 9 in its basic design, and it also borrows from L4, which is a microkernel architecture. And as you might guess, this is a microkernel-based system called Redox OS. It's been around for probably, I would say 4 years, maybe 5. But yeah, it's been gradually building up. It's still in alpha. It doesn't have a full set of things yet, but we're going to look at it. Some of its strengths are with Rust is that it avoids many of the trade-offs that show up inside of monolithic kernels like Linux. Plus, it's an operating system that doesn't have to carry baggage around with it from the past, whereas Linux does. There are devices in there that date back 30 years or more that are still there that someone might still be using. So here's the complete transition that in moving from this this whole debate between Rust and C reminds me of the debate between Minix and Linux many years ago, where Linus had published his code. There was some initial versions of it that were floating around that you could pick up and install with great pains, but you could get it to install and run. And then it was looked at by Andrew Tannenbaum, who was the author of Minix. Minix is a microkernel system, very Unix-like. It's used it had an academic flavor, an academic design. It tried to teach good principles in operating system, how to build a proper one. And so he kind of took Linus to task in the Usenet forums, saying that, basically Linux was not good. It's not living up to the what a modern operating system should be. Well, Linus got mad. He got mad. And so, yeah, they were exchanging blows, and yeah, it got ugly for a while. However, for most of us, it was kind of entertaining to watch it. But, it just, I'm not going to relive all that. But, the, the things that were true back then of Linux are no longer true of Linux. Some of the criticisms that Andrew laid up on it is that it didn't support enough platforms. Well, Linux was getting started. They didn't have a lot of people that were working on, all the different ARM-based machines, or any of the Fujitsu or any of those kind of processors, or even the IBM PowerPC platforms. There wasn't a lot of people working on stuff like that. They had Intel, and that was it, the x86. But even then, it was a real thin. Yeah, you had a specific architecture that you had to stay in if you wanted it to run. Yeah, certain cards, certain drivers it had very little driver support, actually. So yeah, and Linux was monolithic, and Tannenbaum just ripped it apart. But those, the things that were true then aren't true now. Linux has grown into a very large platform supporting all kinds of workloads, from edge and IoT devices all the way up to the largest supercomputers. So yeah, I mean, I think we all know that what Linus was looking at wasn't an academically correct operating system. What he was looking for was something practical that people could use. Imagine that. Yeah, we weren't trying to pass a whole bunch of academic tests. We were just trying to see if we'd get this thing to work and people would want it. The debate was pretty heated, and I think history chose Linux for one simple reason. Performance and practicality usually win out over things that are theory, elegant, and not necessarily the best design, the best purity design. It can look like a mutt, and people will use it. That's just the way it is. But Linux ran fast, and it started to run everywhere today. It's ubiquitous today. So yeah, so the things that Andrew criticized Linus's Linux for aren't really true anymore. So yeah, because the world has changed. As we wrap this up today, I think we need to remember that none of these benchmarks exist in a vacuum. They were all developed for specific purposes. Dhrystone, Whetstone, MemSpeed. There was even LinPack. It was a small light version that was meant for running on DOS, basically. There was Mandelbrot that was crafted as well. And it was people like Roy Longbottom that actually made this happen. He gave his time. He gave his skill. And nobody thanked him. He didn't earn any prizes for this. He didn't get much recognition for it. But people in engineering we all knew who he was, and we knew what he did. In the 70s and 80s, Dhrystones, Whetstones, man, people were quoting what those did on every machine they could find the data for, so that somebody had done the benchmarks for. But Roy didn't stop. He kept refining his work. He kept finding new ways to improve it and adding on new benchmarks. If you go to his site, these all belong to his legacy, but he has new benchmarks that test newer things. And that's why I just started here, because these are ones I'm familiar with. And then he kept that website going. I'll put his link below too. We need more people like Roy, because people without those people, we would never have been able to answer the question. If I'm comparing two different compilers from two different vendors, that's one thing. But what if they're completely different languages? How do you sync them up? And that was the checksum. So that brings us to the last benchmark I don't have ready yet, and that's the Livermoor Loops. This is a stress test. This exposes everything in the compiler that it does. It'll show what it gets right. It'll show what it gets wrong. So it's built for parallelism, and that's exactly what we need, because that's what our systems are built for. they have multiple processors, they are able to do parallel processing. So even though our operating systems are not capable of doing that, they simulate it. But you can use this and gain truth from it. Without going into too much detail, let me just say it this way. It's built up of kernel tests. There's 24 of them currently in there that beat on different parts of the compiler to expose weaknesses. And there's 3 calibration runs that it makes with those 24 in order to, I don't know if it's to heat up the processors or maybe just to try to get it to close on alignment so that we don't have as much variation in floating point arithmetic as we go through it. But anyway, we're going to test that on both C and Rust, and we're going to find out what it does. I don't know what it'll do. We'll find out. I hope is that this will be simple, even though the application itself is a whopper. It's big. So it'll settle, hopefully, the argument is C or Rust better. We have a partial answer, but not a complete one. So I'm not saying which is better until that one is working. I hope you enjoyed this video and this look back a little bit on some of the problems that were solved, and that, whenever you're looking at new languages, drag some of these old ones out. They're designed for that. They're designed to look at that sort of thing. Anyway, I hope to see you in the next video, and please like and subscribe, and bye for now.